can I get your attention? And then I'll get your question after. Question number 1. So I rearranged it so that I could see my A value is a half. We could have left it as it was and still graphed it, but just to put it in that kind of form that we've been learning to understand, I rearranged to see that A value clearly, and then I can see my B value also as a half. So vertically, it's stretched by a factor of a half, does exactly what A looks like. Horizontally, I do the reciprocal, so it's not stretched horizontally by a factor of a half, but by a factor of 2. So horizontally, twice as big. So I get this graph. Good? No questions. Now, as you look at number 2, what do you notice about the stretch factors compared to number 1? Karina? Well, they have a binomial in the numerator, that's the equation, but what about the stretch factors? Prableen? Yes, but what about the stretch factors? Yes. They're exactly the same, which means the shape of my graph for number 2 is exactly the same as the shape in number 1. So I can use the shape I created in number 1 and then just translate it for number 2, because I've already done all the stretching I need to. I'll give you some more time. Let me talk about number 2. So again, I rearranged the equation. I wouldn't have to, but what we're going to be looking at and kind of the generic formula you'll have on your formula sheet is going to look something like what I wrote up here in black and blue and red for number 2. So I started by multiplying the half on both sides, so that's how I got the half in front of my f of x. And then I subtracted the 1 over to the other side. So then I can see that vertically it's going to be stretched by a factor of a half. That's my A value. And it's going to be translated down 1 unit. Any questions with the vertical stuff? Nope. Horizontally, even though I have this x minus 3 and then all over 2, I can rewrite that as though I factored that half out in front and then put an x minus 3 in brackets. So then I can see my B value is a half. So the stretch factor is reciprocal of that. Stretch factor is 2. And it's translated to the right, so again, opposite of what it looks like, by 3 units. So my graph should have that same shape, but it'll be, compared to the green one, it's down 1 and 3 to the right. Any questions with number 2? Yes, Nazifa. Mapping notation. Excellent question. So for mapping notation, I'd say xy. My x's are all doubled. So 2x, and they move to the right, so plus 3. So kind of what's in my mapping notation is the opposite of anything I saw in my original function. Instead of a half, it's a 2. Instead of a minus 3, it's a plus 3. And there are no brackets. Because first I'm stretching, so I'm doing the multiplication order of operations. I'm stretching the x values first, then I'm translating them. Yes? That's right. So translating is not affected by the vertical stretch. Okay, then the y does exactly what it's looking like. So I have the function times a half. So I have a half times y. And then the minus 1 at the end means it's translating down. So that's what mapping notation would look like for this question. Okay. Before we get too far on the next two, I want to talk about number 4, and then I'll give you more time. You have a question before number 4? Mapping notation for 1. Yes. xy is mapped to. All the x's are doubled. All the y's are halved. Was that in the instructions here? Oh yeah, described using mapping notation. I should read my instructions. Okay, yes, Chef. Well, with practice, we can do it from the equation as well. We just know it's doing the opposite. So typically what I'll do is I'll think through what's happening. So this half tells me, oh, the reciprocal is 2, so it's stretched horizontally by a factor of 2. That's where I'm getting that 2 from when I do the mapping. So I kind of go through the description in words in my head to the mapping notation. Yes, Pauline. Yeah, that's what I'm doing in my head, even if I don't write the words down. So I think about in words what's happening horizontally and vertically, and then I use those words to write out the mapping. Okay, number 4. So this is another one where that we looked at something similar yesterday, I think, where I have 3 times x and then the minus 15. Because I have something multiplied to the x here, I need to factor it out from both of those terms inside the bracket. Otherwise, I'm not going to get the correct translation. So I would rewrite this. Y equals -2. F, my b value will be a 3. When it's factored out, I'll have an x minus 5. So this way, I can see that it is translated 5 units to the right. It's not 15 units to the right. Yes. So imagine that my function originally was, and it wasn't this, but suppose it was y equals the square root of x. If that was the original function, and I wanted to rewrite this in that form, I'd have the -2 in front, so y equals, and then I'd have the -4 at the end, and then I'd have the square root of 3 times x minus 5. But this 3 and the -2 I can't multiply together because the 3 is inside a function, something's being done to it. So up here, because I don't know what my function is, there would be some functions where I could take this out and multiply it to that, but many functions where I couldn't. So I can't assume that I can multiply them. I rather assume that I can't, and then I just see what happens if I have to keep it inside. Yes, Roger. I want it to have a coefficient of 1 in front of the x, because it's only once I do that that I can see exactly what's happening. Otherwise, I end up with the wrong translation factor. My stretch will still be the same, that b value is still a 3, but I get the wrong number for my horizontal translation. Yes, Saad. Well, I do have an x value of 0 here. You mean once I draw the whole thing? Well, it's just responding to the different stretches and reflections and translations that are in there. And where it ends up, it ends up. And in this case, because we're combining transformations, we're not ending up with any invariant points. If I was only stretching, there could be some invariant points. If I was only reflecting, there could be some invariant points. But as soon as I start translating, there aren't any invariant points because every point is moving. Yes. Sorry, say that again. The 3 1/3. When I write the mapping, it'll be a third. My B value is a 3. So that is what B is. My stretch factor is 1/3, but it doesn't show up as 1/3 in the equation. Yes. So the points, x values would be multiplied by 1/3. Let me pause. So I skipped a little bit in the video, but they're the first two stages. So I'm repeating this for people online. There we go. The blue part is the reflection. So that's the negative sign from the equation at the top. And the green graph is the vertical stretch by a factor of 2. Finally, the 3 times x means all the x's are multiplied by 1/3. So we end up with this graph. So this point over here, what was it? -6, 1/3 is going to put it at -2. This point here that was at an x value of 6, 1/3 is at +2 over there. Question? Why? Isn't it beautiful? Okay, fine. We'll get rid of the other two. This is what the final graph would look like with a bunch of circles. Whoops. Is that good enough? Okay. We could do it all at once if we wanted to do point by point and think about the mapping notation. So let me just talk about that briefly. If we wrote out the mapping notation, the only thing done to the x's is they're stretched by a factor of 1/3. So I'll have 1/3 times all my x values. And then for my y values, the sign changes and they're doubled. So -2 times y. So then, if I just picked a point, so I'll just do it for one point, but you could do it for all the key points. Let me do it for this point here. So what would I do? I would use this point, this one, and that one, because those are four are kind of the key points for me to get the shape right. If I just look at this one, that's -3, comma 1, 2, 3, 4, -3, comma 4. What's happening to that point? -3 times a third gives me -1. 4 times -2 will give me -8. So that gives me this point, -1, comma -8. So I could just jump right to plotting that point from using the mapping. So sometimes that's what people will do. They'll just do a little table. And in their table, they'll have the original ordered pairs listed out. And then so this would be the x, y. And then over here, we'll do the 1/3 x times -2y. And then they would just list out what's the resulting point that we get. So that's an option for doing these as well. Again, as I mentioned yesterday, the advantage of this is you're kind of doing the hard work at the start, where you figure out the mapping. And then it's not really hard to plug in numbers and find the points. And then you just stick the points on the graph. Where the problems come in is if you make a mistake in plotting one point, recognizing it, or forgetting what order you're supposed to connect the dots. But it's a perfectly valid and good way to do it. I would like to push understanding the stretches, reflections, translations, so I generally don't, but you don't have to do it my way. There's more than one way to do it. Questions? Nope. Okay. So for the last one, we have the shape, same as the red one in number 3, It's just the whole thing is translated 5 units to the right and 4 units down. So we end up with 5 to the right, I think is about there, and 4 down. Questions? Nope. If we did this one by mapping, so suppose we didn't have question 3, and we just wanted to do question 4 kind of all at once. If we wanted to think about the mapping, I guess I need to be able to see that. I will make a little box here. Okay, so in here I will write my mapping notation. So I'll have xy, what's happening to the x's, they're multiplied by 1/3, and then translated to the right by 5 units. The y values, reflected and stretched by a factor of 2, and then translated 4 units down. Questions? Yes. No. You can just do it in mapping notation. So you can expect no calculator part to the test. Or I give you something like number 4. I give you the graph, I give you an equation, and you need to sketch what it looks like. Okay, next page. Here for each of these equations, we want to describe the transformation. And when we're describing it, we always want to describe translations last. For stretching and reflecting, the order of those doesn't really matter. But to make it simple, I say just do it alphabetical order. Reflect, then stretch, then translate. As long as the translation is last, then we're good. And so then we're going to state the domain and range of each of these transformed functions. So, number 5, reflections. Rishav, could you tell me if there are any reflections in this function? It's reflected on the x-axis. Yes. So the negative out front is changing y values, which means it's reflected in the x-axis. Thank you. Stretches. Sadeeb. I'd agree with that. And then translations. Nadi. Down 3. I'd agree with that too. So we want to state domain and range as well. So it's going to be helpful for us to think about the original domain and range, as in the original function is y equals the square root of x. So if we just think about it once, then we can use that for all the future ones. So if we talk about the original, for y equals square root of x, original domain, Denise, could you help me? For the original function. So we're not looking at the transformation, just the square root of x. Or if you'd like, I could ask somebody else. Could I? Okay. Feel free to tell me that if I ask you a question. Neat. what would you say? Could you help me with what's the domain of that original function? 0 to infinity? Yes. What should my endpoints look like? So I include the 0, that's not a 6, but I don't include infinity because I never reach there. Yeah. So from 0 to infinity, including the 0 but not the infinity, that would be my original domain. So right away, let's do the image or transformed. So it's stretched horizontally by a factor of 1/4. So if I think of multiplying 0 by a fourth, it's still 0. Infinity by a fourth, believe it or not, is still infinity. So that doesn't change it. Has there been any other horizontal change to my graph? Nope, just that. So my domain is exactly the same. Rabia, can you say that again? Yeah. If we were to look at the graph, we would get a function that starts here and then curves up like this. And so looking at that graph, that can actually help us with the range here on the original also from 0 to infinity. Mine kind of like looks like it's going horizontal, but it does keep going up forever, including the 0, not including the infinity. So my range for my image, well, maybe I shouldn't put bracket there already. So what does the reflection do to my range? Kabir? So it's going to curve down this way. It's going to go in the negatives. So I'm going to switch these and I'm going to have negative infinity. Well, I'm not going to write that there yet. I'm going to write it down here as sort of a transition. Negative infinity, I can do this, up to 0. Okay, so that's just the reflection. And then there's no stretch, but there is a translation. So then I'm going to translate, translat E, and it's going to go down by 3. If I decrease negative infinity by 3, I still get negative infinity. Because again, it's not actually a number, it's just further, it's an idea. And then decrease the 0 by 3. So that's what my range would be, negative infinity up to negative 3, include the negative 3, not the negative infinity. So there's my new domain and range. So as we did it, we kind of thought through the stages. So we thought through, okay, what does the reflection do? And I wrote what my range would be. And I thought, if there was a stretch, I'd say, what does the stretch do? And I'd write down my range. And then I'd say, what does the translation do? And I'd write down my range. That's one way to do it. Or we could have gone back and said, what would the mapping look like? And then use the mapping to just jump right to the new range. Let's not do that for this one, but let's do that one for another one. Any questions on number 5? Yes. I don't know. I actually haven't looked for the infinity button on the calculator. So, I don't know. Yes. would say any of these on this page, you could do without a calculator. Like, I would expect for basic functions that you would know the domain and range. As in, I'd say, that's a fairly basic function, a radical function. I'd expect you to know probably what 1 over x is like, what x squared is like. Let's see. We have only 3 minutes, not much time. So let me just whip through the next one. No, whip through the next one. No, we shouldn't rush things. We need time to think things through. So we will come down to the summary. And we'll fill this in, and then we'll come back and finish off this lesson tomorrow. A variety of vehicles here. So you were given this equation on your formula sheet. You're not told what anything means. We just need to know what it means. So if there's a reflection in the x-axis, which of these letters, A, B, H, or K, tells us? The what? A. Here we go. If A is less than 0, then we have a reflection in the x-axis. Reflection in the y-axis if B is less than 0. Oh, we got a gong, a soft gong. Could have done this one next time. Okay. Vertical stretch factor. What am I looking at? A. Is it the A value? Absolute value. Horizontal stretch factor. I'm not hearing a unified statement there. Let's try this again. Horizontal stretch factor, 3, 2, 1. Again, that wasn't all the same. I can't give you anything for that, sorry. 1 over the absolute value of B. So it's not just the absolute value of B. On to our little ice cream truck. Oh, well, here the stuff is easy. So the vertical translation factor. Oh, does this work? Oh, it does. Horizontal translation factor. Yes, H. There we go. That'll do it for today. Thank you.